Okay, so let's just dive right in. Digital signal processing DSP. I mean, it's basically this invisible force, right? It's running almost every piece of tech you touch, from your phone to your car to all those IoT devices.
Really is.
But there's this hidden cost, a fundamental bottleneck that's holding back how fast and how power efficient all that tech can be.
And if you really peel back the layers on that whole process, the bottleneck, it always comes down to one thing: multiplication.
Always multiplication.
Yes. Whether you're talking about, core DSP stuff like FIR filters, finite impulse response filters, or these huge deep neural networks, multiplication is the heavy lifting. A general purpose multiplier on a chip takes up a ton of space. It just guzzles power, and its complexity, well, it basically throttles the whole system's clock speed.
So if you want longer battery life or faster apps,
Yeah.
you have to find a way to kill the multiplier.
You have to kill the multiplier.
Yeah.
Exactly.
And that, I think, sets up our mission for this deep dive perfectly. We're going to track this hardware revolution, how engineers are just ditching these complex, expensive silicon multipliers for circuits that only use incredibly simple things: additions, subtractions, and shifts.
And it goes even deeper.
How so?
It's what happens when you stop designing the math first. When you start designing the filter itself to take full advantage of the really cheap hardware you want to build.
A total
A
co-design.
total co-design. And we're diving into research that uses some really heavy-duty modern optimization to do this, specifically a technique called integer linear programming, or ILP, to find what are truly optimal multiplierless designs.
And when you say optimal, you don't just mean better. You mean mathematically provably the best.
The absolute best. This isn't just a small step up from the old methods. We're talking about guaranteeing the absolute minimum hardware cost, something that, was just computationally impossible for real-world shelters until very, very recently.
Okay, so let's start with the foundation. The fundamental trick, because it's actually surprisingly elegant.
It is.
In a DSP system, the numbers you're multiplying by, the filter coefficients, they're almost always fixed constants.
Hmm.
And the big trick is realizing that any multiplication by a constant can be completely replaced by just a few shifts and adds or subtracts.
And this is where the whole cost structure of hardware just gets flipped on its head. In silicon, a bit shift, moving a number left or right, is essentially free.
Free! How can it be free?
Because it's not a logic gate, it's not a calculation, it's just wiring. You're just routing a wire from one spot to another. So the only thing that actually costs you anything, the only currency that matters, is the number of adders and subtractors you use. We call that the adder cost.
Okay, so the sources have a great simple example of this. Let's say you need to multiply a number, we'll call it x, by 23.
Right, without a multiplier.
Exactly. No big clunky hardware. Instead, you could say calculate x times 2, add the original x back in, which gives you 3x. Then you shift that result 3 places to the left, which is the same as multiplying by 8, and now you have 24x. And then you just subtract x.
And there you go, 23x. The mathematically exact result, and you only used one addition and one subtraction. You've replaced this huge, power-hungry silicon block with two simple arithmetic units and, well, some wires.
That's the core idea. But obviously, the real world challenge gets a lot bigger than just one number, right?
Oh, absolutely. That simple example is what we call single constant multiplication, or SCM. And believe it or not, even for just one single large constant, finding the guaranteed minimal adder circuit is what's known as an NP-complete problem.
So it's one of those mathematically hard problems.
Incredibly hard. It means for really big numbers, finding the absolute best combination of shifts and adds is, well, it's often practically impossible without just a massive amount of computation.
Okay, so SCM for one number is hard enough.
Yeah.
But real filters have dozens, maybe hundreds of these coefficients.
And that brings us to the real problem everyone's trying to solve: multiple constant multiplication, or MCM. An FIR filter takes one input signal and multiplies it by a whole set of different constants all at once.
Right.
The beauty of MCM optimization is that you can calculate an intermediate sum, like that 3x we just made, and then you can share it. You can reuse that result in the calculations for a bunch of different coefficients in your set.
Oh, I see. So if I needed to make coefficients like 7 and 12 and 23, maybe they can all use a piece of the calculation for, say, the number 3 or 4.
Precisely. If you calculated each one on its own, your adder cost would just explode. But by sharing these partial products, these intermediate steps, you can compute all of them with a dramatically lower total number of adders. That's the real magic.
And for anyone designing these systems, the key thing to know is that this optimization works no matter what the filter's high-level structure looks like. You have these direct form filters and transposed form filters.
Right, but for a single input, single output system, the underlying math is the same. When you optimize that MCM block, you've optimized the whole filter. It really simplifies the problem so you can just focus on that one goal. Minimize the arithmetic.
So for a long time, engineers were basically just guessing at this, using educated guesses.
Pretty much. Historically, finding that true minimum relied on heuristics. They were clever and often very good, but they could never, ever guarantee you had found the actual mathematical optimum.
I remember the most famous one was canonical sign digit, or CSD.
Hmm.
That was a huge deal because it automatically cuts down the number of non-zero digits you have to deal with in a number.
It was a brilliant, greedy algorithm, really. It just makes sure no two consecutive digits are non zero, and that naturally reduces the number of ads you need. On average, it brings the operation count for a number from, say, half the number of bits down to about a third.
But it's a local optimization, isn't it? It's only looking at one coefficient at a time.
That's the weakness. It's not looking globally at the whole set of coefficients to see, how you could cleverly reuse parts. So, researchers knew a globally optimal solution had to exist, the absolute lowest possible adder count. But with heuristics like CSD, you were always settling for pretty good.
And pretty good isn't good enough if you're shipping a billion mobile phones.
Not even close. You need absolute optimality. And that's where these modern optimization tools finally give us the breakthrough.
So we're moving from heuristics to guarantees. The big leap forward is using the power of integer linear programming, ILP, to find the true optimal multiplierless design for these big complex FIR filters.
It is, but it requires some finesse. The researchers developed two different ILP models, basically, because when you're designing hardware, you have these two competing goals.
Which are what? Minimizing cost and maximizing speed.
Essentially, yes, area and power. The first model, ILP Formulation 1, is all about area. It solves the problem by fixing the number of adders inside the multiplier block itself. Let's call it A sub m. And then it minimizes all the other structural adders needed to put the results together. It just keeps trying until it finds the absolute lowest total adder count.
So that gives you the smallest, cheapest possible chip. What about the other side of that coin, the speed and the power?
That's where ILP Formulation 2 comes in. Power consumption is often really sensitive to something called adder depth. That's the longest chain of adders one after the other. If you have to wait for, say, 5 additions to happen in a sequence, that's going to limit how fast your clock can run.
I see. It creates a delay.
A critical delay.
Yeah.
So ILP2 lets you set a hard limit on that adder depth. You're telling the solver, I care more about speed and low power, so don't even consider solutions that are too deep.
So you're making a classic engineering trade-off. We're trading a bit of area for a boost in performance.
Exactly. Sometimes that bounded depth means you get a slightly higher total adder count than the first method, but you get a guaranteed high-speed, low-power design. And we should be clear, solving these ILP problems, it's a huge computational lift.
Yeah.
For large filters, we're talking about running these solvers for days before they can finally prove they've found the single best configuration.
Wow, days of computation. That really puts the cost-benefit analysis in perspective, doesn't it? You're trading this massive one-time upfront compute cost to guarantee just a tiny bit more efficiency in every single chip that ever ships.
It totally validates the effort. And this whole shift towards guaranteed optimal design enables what the sources are calling Revolution 1 in hardware design, the co-design flow.
Right, because the old way was so sequential. You do the math in MATLAB or something, get your perfect coefficients, and then you try to figure out how to build the hardware efficiently.
You'd basically throw it over the wall to the hardware team and say, good luck. The new co-design approach is holistic. The goal is to find the set of integer coefficients that meets your frequency specs and requires the absolute minimum number of adders all at the same time. You optimize them together.
And because it's using these guaranteed solvers, this co-design approach has uncovered some genuinely counterintuitive results. The one that really jumped out at me was about filter size versus cost.
Yeah, that one goes against decades of engineering intuition. You'd always assume that a higher order filter, a bigger, more complex filter, has to be more expensive, it has to cost more.
Of course, more taps, more coefficients, more cost.
But the optimal design process shows that sometimes increasing the filter order n can actually reduce the total adder cost.
Well, hey, hang on. How does making it more complex make it cheaper? That seems completely backwards.
Because the goal isn't just a smaller filter anymore, the goal is finding a set of coefficients that are mathematically sparse and highly shareable. A slightly higher filter order might open up a new mathematical space where a solution exists that reuses intermediate sums much more cleverly. You're accepting a bigger model to unlock a much more efficient hardware implementation.
It's like finding a solution where the number 3 shows up a bunch of times, so you only have to calculate 3 times the input once.
That's a great way to put it.
Mm.
And another thing is the flexible gain factor. When you give the solver just a tiny bit of freedom on the overall filter gain, letting it vary between, say, 2/3 and 4/3, it dramatically improves the results.
Why is that?
Because a fixed gain requirement is a very harsh constraint. It severely limits the number of possible coefficient sets. As soon as you loosen that just a little bit, you open up this huge new design space, and it becomes much easier for the solver to find a solution that is both sparse and incredibly efficient.
So this isn't just theoretical. The experimental results in the sources show this co-design approach has a massive advantage.
A huge advantage. For one complex reference filter, S2A, this optimal co-design got a 30% reduction in the adder count. It went from 116 adders down to just 81. And what's more, it also reduced the number of bits needed for the coefficients from 13 down to 10.
Wow. So it's less circuitry, less complex, less power, and it still meets the exact same performance spec. That's incredible.
Another benchmark showed a 23% improvement, and this is all being automated now. There was a case study where they optimized part of an MP3 decoder, the DCT and IMDCT blocks. By automatically tuning the precision to meet the official standard, they cut the adder cost by 17%. It proves you can automate these optimal choices based purely on what the application actually needs.
And that idea, designing for what you actually need, that leads us straight into Revolution 2. We've just spent all this time talking about how to get mathematically exact multiplication with the cheapest possible parts. And now, the whole industry is pivoting again, this time to embrace, well, intentional imperfection, approximate computing.
Yes, this is the big paradigm shift, and it's a really important distinction for you, the listener, to grasp. Revolution 1, multiplierless design, is exact. The math is perfect. Revolution 2 is the realization that for a lot of modern apps, you can use the simplest, lowest power hardware that is just good enough, even if it makes tiny mistakes.
And why is it suddenly okay to make mistakes? The whole point of a computer used to be that it was perfect.
Because so many modern workloads are inherently error tolerant. Think about image processing or machine learning or video encoding. If a single pixel's color is off by a tiny amount or one calculation deep inside a neural network is slightly inaccurate, you'd never notice. The final result is often indistinguishable to a human or to the system as a whole.
So you can trade a tiny, unnoticeable error for a huge win in efficiency.
An immense win. And it's not just one trick, it's a whole family of strategies that get applied at every level of the design.
Okay, let's break down those levels. Where does the approximation actually happen?
Well, at the highest level, the algorithm level, you just rethink the entire calculation. Instead of standard multiplication, you might use, say, a logarithm-based approach, which is fundamentally approximate, but also incredibly fast and simple.
Okay, then you move down a level to the actual chip design, the architecture level.
Mhm.
How do you approximate a multiplier there?
This is where it gets really clever. You can actually modify the multiplier stages. For instance, imagine you have a 12-bit number. The first 8 bits, the most significant ones, are critical, but the last 4 bits, less so. So you can build a circuit where the parts that handle the most significant bits are exact, but you replace the components for the less significant bits with simpler, faster, approximate versions.
So you're literally building a multiplier that is perfect for the bits that matter most, and just good enough for the bits that barely affect the final answer.
Exactly. You slash the area and power of that circuit, and the impact on the final accuracy is often negligible. And then finally, you can go all the way down to the circuit level, the logic gates themselves, and use tools to prune or rewrite the Boolean logic to use the absolute minimum number of transistors.
This all sounds like it should add up to small, marginal gains, but the results in the sources they're anything but marginal.
The payoff is staggering. In complex tasks like image classification on standard datasets like Skyfar 10, the research shows that many of these approximate multipliers delivered more than a 75% improvement in energy efficiency.
75%.
Yes, massive reductions in power and delay, all while losing less than 0.5% in classification accuracy.
That's the sweet spot, defined perfectly. A monumental gain in efficiency for a loss that is, for all practical purposes, zero. That just fundamentally changes how we should think about performance.
It does. Our whole deep dive today really shows the full evolution of this thinking. It started with simple gate-level tricks, Then it matured with CSD and MCM to get these highly optimized but still exact results.
Then came Revolution 1, the automated code design that squeezed out every last drop of inefficiency to find the true mathematical minimum cost.
And now, finally, Revolution 2, where we just embrace approximation. We trade these tiny, controlled inaccuracies for massive gains in speed and energy, especially in fields like AI. It's a journey from brute force to intelligent design.
It shows that maximizing performance isn't about raw power anymore. It's about intelligent resource allocation and, I think, knowing precisely where perfection is just too expensive to be worth it.
That's the key.
This whole push for optimal error-tolerant computing really makes you think that the highest performance systems of the future might be the ones that are meticulously designed to be just inaccurate enough. So think about this. How many applications in your own life actually demand mathematical perfection? Your banking app, maybe.
That's one for sure.
But how many just need to be good enough? Streaming a video, recognizing your face to unlock your phone, a photo filter. That question, I think, is going to define the entire next era of hardware design.